Good morning, guys. Today we're going to learn about the logistic regression, which is part of the supervised machine learning. Just like is the name is the regression, doesn't mean it's working same as a regression. They just give it a name because it derives the principle from the regression. So let's go and see. So as I already told you in our previous class, that the supervised machine learning is further divided into two main categories. So first one is regression and then the classification. In the last theory class, we teach you how the regression is being done and how the parameters are determined by the regression model. So in this lecture, we're going to learn how these regression models can be useful for the classification, which is logistic regression. So it's basically the regression model, but with some new functions which allow you to classify your samples. Either it's belong to the class A or class B, and so on. So the idea of the logistic regression is that when you are doing a regression, you always have the continuous values. So your sample, which means that your X and Y are continuous. This doesn't matter. It could be anything. X could be anything, either in regression or classification, but the models are chosen based on your Y, which is your outcome. So we say your outcome should be continuous. So what the continuous means that you do not have a defined boundaries for any group. So your group can contain any value, like infinite values from 0 to infinity. Okay, it can also go beyond. Okay, so for example, in this example, if we are measuring the temperature of any day, so this could be the continuous values, because your temperature can exist in any number between 0 to infinity. Okay? In the classification, we are actually set in a boundary. Okay, so we set a boundary to classify our samples. So for example, here what we are doing in the classification is that instead of going to the continuous, here we also have continuous values, but we're going to divide those values into groups. So here I am saying that the temperature will be called if it's below 80. Okay, so this is my first group. Here I made first group, and if the temperature is start from the 80, then we should classify it as a hot day. Okay, so now we have two groups. Here in the regression model, you can see that we don't have any group, but you can see that you can know about the weather by just predicting the continuous value. So here, for example, if you are taking this 84, okay, you can say based on this result that since it's about 80 is going this way, so this is more similar to hot day. Okay, so this regression will be classified into hot day. Okay, here. So let's see how the regression are being converted into the classification models. Okay, so this is done through the logistic regression. So first of all, I want to emphasize that the logistic regression is basically derived from the regression models. So in the regression model, you will have the probability, okay, of the feature in the class Y. Okay, so here this is your feature, as we already told you in previous class, and this is your outcome. Okay, so in the logistic regression, we usually measure the probability of X present in Y. Okay, and this is done by like taking. So, for example, in our data, we have class Y, which contain two categories, and we assign them for 0 for normal and 1 for KEGG answer. And then you have to take that in the normal, if this X is present, okay, so what is the probability of this X to be present in normal, and what is the probability of this X? It could be feature or any gene or any biological relevant thing that you can measure, okay, in normal and cancer patients. So you're going to take probability and you're going to use it for binary classification. As I already told you that for logistic regression, we need binary classification. So that means that you have to convert your labels, your samples, divide into the groups. Okay, so groups will come from your data. Okay, so you take the probability and you have to analyze that if features will be present in zero class or one or present in both of the classes. So you want to basically know the importance of X in the normal or in the cancer. Okay, so in the logistic regression, as we saw that in the previous video, we were doing line of the linear regression like this, and we were fitting the line, which was determined by the B0 and B1, which we said it was the parameter. So there we were fitting the straight line, which were like optimized to cover all your points and minimize the errors, okay? Distance between predict value and your trend value. But in the regression model, logistic regression model, what we do is that we don't draw the straight line. Instead, we draw this S curve, which is called sigmoid. Okay, so it is called the sigmoid function. So later we're going to see that what is this sigmoid function. So what it's going to do is that, for example, in the linear regression, you have like continuous value, and here also continuous value. But in the logistic regression, what you do is that you, in your here y-axis, you're going to put here, for example, 1, and here you're going to put 0. Okay, so this sigmoid function will allow you to classify your sample based on your probability. Okay, later we're going to see, don't be confused. So what sigmoid function do is that basically it take this line and convert it into S shape, which we say the S curve. Okay, so where you're going to draw your decision boundary here. So we're going to put our decision boundary 0.5. This is the standard, but you can change it, of course, depending on your maybe objective of the study or whatever. But usually by default, it's taking like this. So in your decision boundary, we're going to take like this, 0.5, and we're going to draw the line. Okay. So what this decision boundary is telling you is that if the sample falls here, this will be your zero class, okay? And the zero class is normal. So if your unknown sample falls below 0.5, it's going to be classified as normal. If your data end here, okay, so this will be classified as cancer. And how we determine is basically we are drawing the line which allow us to distinguish between the samples. Okay, so later we're going to see that how these values are taken and how the classification is being done. It was just introduction here. So we say that to do the logistic regression, we need a probability of X sample, X feature. Okay. So what is probability? Probability is basically the outcome of your interest. Okay. If you want anything, if you want any event to be occur in the time and space, so you are interested in that event. Okay. So you're gonna say that this is the outcome of interest I want, or what are you analyzing, divided by all possible outcomes. Okay, so this is the formula of probability. Here is the outcome of your interest, and here is the all possible states of your event. So let's see with a finite number. Okay, so for example, here this is the coin. Okay, which have two possibilities, head and tail. Okay, so I want to know that what is the probability of heads when I throw a coin in the air. So if head comes, I win. If tails come, I lose. So I am interested in the heads. Okay. So, and I want to know what is the probability of my winning. What is the chances that I'm gonna win this any situation? Okay. So, for example, I want the head. Okay. So that represents one represent head. Okay, because I want one. I cannot get head and tail at the same time. We are not in quantum physics, so in the quantum physics, okay, you have all the states possible together, but here in our real world, in a classical physical world, we only have like probability of event that is occurring. So this is one chance of head divided by 2, because we have like two possibilities, head and tail. Okay, so my possibility of head and tail, my possibility of getting head is 1 divided by 2, which is if you simplify it, it's gonna be 0.5. And if you like, so my probability of winning is 50%. Okay. So chances are that if someone challenges me and say that I throw a coin and if you get the head, you win. If it become tail, so he gonna win. So what are my chances of winning is that 50%. Okay. So if you multiply these events, if it's the all possibilities, you get always one. So probability is always between 1 to 0. Okay. So probability cannot go after 1 and cannot go below 0. Okay. So event occur or event dot occur. Okay. So there is no negative probability or after one probability or infinity. So we always have to keep the probability into this range. Okay. So my chance of getting head is 50%. Okay. But when I throw a dice roll, okay. So here is the die roll. So if you want any number uh, that will allow you to win, you can choose from 1 to 6 any number. Okay. So you're gonna say that, okay, what are my chances of winning with the die roll? Okay. So here, if you calculate your probability, you can say that you want one outcome, which is your outcome of your interest, and all possible outcomes. So here, what you do is that you have 6 possible states of this roll die, and the one is you are interested. Okay. If you simplify these, you will get this answer. As I told you, that our probability will always be in this range. Okay. So if you are like, what are the chances of my winning? Is that 60%. Okay. So if you convert this number into 60, if you convert into percentage, you have to do like and multiply by 100, and you get 60% of chances. So here you see that in the heads of the tail, I had 50% chance of winning, but in the roll die, I have only 16% of chance that I'm gonna get any of my desired number. Okay. So as the states of any material or any outcome increase, so your outcome of interest will be diluted with all possible states. Okay, because you have many probabilities together. You have many states of any object to get, so your desired outcome will be diluted. Okay. So in this case, if you again do like 16 multiplied by 6, you will get 1, okay, which is the maximum probability. So here what it is telling is that there are 100% chances that you get any number of all six states, okay, but only 16% chances that you get your desired number, okay, because all our states are 6. So you have either you throw the roll die anytime, you get the number between 1 to 6. So that's how the probabilities are being done. So how it is important to do in the logistic regression, how we use it, we're gonna see now. So in addition to the probability, we use odds, which is same like the probability, but in the probability, we just say that what is the chance of our outcome of interest happening in the time, okay? But in odds, we can say that, okay, we can also take to analyze the risk of the event that are not happening. So for example, odds can be calculated as the probability of event that occur, and that probability will be minus from the all states. So for example, in the coin flip, we have probability of heads, getting heads is 0.5, but that 0.5 should be minus from the overall states. Okay, it's overall probability. So from the overall probability, the 100%, we are getting the 1, which means the 1. Okay, so there are 2 states basically. Okay, so this will not affect any outcome of the interest. But see in the odds of dice roll. So here, for example, you have 16% chance of getting one number out of 6 possible states, which makes the 1 probability. of all events, which we saw previously. And if you minus by probability of one number, you get that there are like 60% chances that you're gonna win the game, okay? But 84% chances are that you're gonna lose the game. If you don't get your desired number, you're gonna lose the game. So here in the odds, we can see the risk of any event, okay? So risk in outcome. So for example, in the probability, we were just saying that, okay, this is the probability of coin getting head is 50% and getting 1 point is getting for the one number in the dice is 16%, okay? But here we are actually measuring also the risk of losing with the winning. So how it's gonna be used to make the decision is that we're gonna do it by odds ratio. So in odds ratio, we get odds 1 and odds 2. So which usually are the odds 1 formula, where we say that the probability of event of interest and the probability of interest minus by 1. Okay, 1 is the all possible states, all possible events that could occur. If it's occurring 100%, it's a 1. Okay, so now someone says that you have to choose the game between coin flip or the dice roll. Okay, so what you have to do is that you have to compare the risk of losing and winning. Okay, so if you put here the risk is like 0.5 for no sorry 1 over 0.2. Okay, so if you divide these numbers 1 by sorry, I'm doing 1 by mobile. So if I do this, I'm getting the score of 5. Okay. So that means that the advantage of the coin is 5% higher than the dice. Okay. If you choose to play with the coin, you will have 5 times more chances to win a game than the dice one. So let's make a scenario here. So for example, here in the coin, we flip the coin in air for 10 times, and out of 10 we get 6 times head and 4 times tail, which leads us to the failure or lose the game. So if you want to know the odds of these numbers, what you're going to do is the outcome and the outcome that didn't, the event that didn't happen. Okay, so here if you divide 6 by 4, you get 1.5, which means that there are 1.5 chances, more chances. Okay, so 1.5 is not a person, but it's a times. Okay, so 1.5 more chances that you're gonna win the game. Okay, so 1.4 more chances over losing. Okay? If you see that in the dice roll, so here you have 6 possible states, and you are rolling the dice for 10 times, you get just 2 times the desired number and 8 times failure. Okay, because you have many states, it's not possible that you get every time the same number. Okay, so here in the host dice, if you are saying that you get 2 by 8, so your chance is like 0.25 of the winning. So remember that the odds of 1 above 1 is more likely that event gonna happen. Okay, more likely. Okay, so this is more likely if it's above 1. So this is more likely that you're gonna win. And here is a 0.5% chances likely not equal to win, likely to lose the game. Okay, so you are not by the dice roll, you are not going to win as you're gonna win by the coin flip. So in this case, for sure, you're gonna choose the coin flip because it's giving you the more probability of winning the game, and winning the game is your desired outcome. Okay, so you want your desired outcome. So in the odds ratio, as I already told you, that we are comparing two groups or two odds. So here, for example, we put the odd of winning a game with coin flip. Here you can say is C, coin flip. And here you can say that it's dice, is dice, okay. So what are the odds of selecting the game? Is suggesting us 6, which means that if you choose the flip coin to win the game, you have 6 times more chance to win the game, okay, by risk ratio, okay. So probably you're gonna choose the coin because it gives you more 6 times success rate than the dice, okay. You can also do by the cross product. Here I'm not emphasizing that. So only just wanted to show you that this can be done and what is the goal behind odds ratio. Okay, I'm gonna erase this so we can do something with our data. Now you know that what is the odds probability and odds ratio and why we use it. Now we're gonna see that how these are important to analyze our biological data. Okay, so now let's do this. This data is synthesized by me, so it's not actual data. But here is just, I take example to show you how these techniques are used to analyze these data and then to classify these samples. So here I made the data for now I am saying that the biomarker yes and biomarker no looks okay. So we have 2 events in overall, and biomarker yes means the mutation in p53 gene, okay, and biomarker no x is equal to 0 means mutation not mutated p53 gene, okay. p53 is the main driver of holding the cancer, is a tumor suppressor, okay. Here I have data, so when the patient get p53 mutated, out of 50 patients, okay, so with p53 mutation, 40 develop disease and 10 didn't develop cancer, okay. Disease means cancer here. And with not any mutation in p53, 20 patients develop cancer and 30 samples or patients didn't develop any disease with no mutation of p53. Okay, so these are the total healthy. They don't have any problem, but these have problem. They have cancer, but absent the mutation. Okay, and so mutation is absent in this group. So now we have overall 100 samples. Now I have to see if the p53 is important to classify these patients, or p53 is playing role in development of disease, and what is the risk of patients with p53 mutation developing a cancer. Okay, so what I am gonna do here is that I'm gonna first take the probability of p53 mutation in my both groups. So for example, first I'm taking the probability for x0, okay? So here you can see that 20 is the event that occurred, okay? So this is the event of my interest, which is occurred, which is cancer, and these are all possible states, okay? So all possible states are like 50, and our outcome is 20. If you divide by these 20 by 50, you get 0.4, which means that there are 40% chances that patient gonna develop cancer without mutation of p53. Okay, and so here's the probability of disease development, okay, without p53 here. And same I do for the mutation present, which is x is equal to 1. So here you can see that our outcome of interest where people develop the cancer is 40, which comes from here. And the total possible events are 50. So here is the 50 are total events. Okay, when you divide it, it's 80. So which means that 80% of disease development chances are in those patients who have P53 mutation. So this makes P53 important, no? Because 80% of people are getting the cancer with a mutation of P53. So that give it an important role in biology. So we have now the evidence to investigate more in the TP53. Okay, so these are the initial evidences we get. So now I'm taking the odds. Okay, so odds is as I already told you, is the risk analysis, risk assessment of developing a cancer or any condition. Okay, so in the odds, for example, if the mutation is absent, what we do is that there is a 20 patients from here which develop the disease, okay? And here are the 30 patients that have no mutation and no disease, okay? So it's a 2 by 3. So odds of developing a cancer with no mutation of P53 is 0.6, okay? So which means that since we said that if it's going above uh, above 1, uh, it will tell you that it's more likely to develop a cancer, okay? And P53 here is going below the 1, which means the absence of biomarker, absence of mutation, okay? Absence of mutation have a protective effect on the development of cancer. So if patients do not have the mutation, they are more likely to be a healthy person, okay? So the chances are 2 by 3, okay? So here are like the times, as I told you in the odds ratio, is that we have the 2 by 3 times risk of developing a cancer. So 3 times is that you are healthy, okay? And 2 times we develop the cancer, okay? So it's 2 by 3. So in every 2 success for every 3 failure, okay? So if the 5 patients come to you with no mutation of P53, you can expect 2 will have the cancer and 3 will be healthy, okay? So it's not a much risk for now, at least, okay? Instead of no mutation, we have to see what is the mutation risk. If patients develop the mutation, what are the risks? So odds of having mutation is 40 of 10. Okay? This comes from here. Okay? 40 event occur and 10 event didn't occur. Event is a mutation. Okay? Oh no, sorry, event is a cancer. So with having the mutation, 40%, 40 people develop cancer and 10% didn't develop cancer. So the risk is 4. Okay, that means that the risk is 4.1 because, for example, here if you cancel this 4 and this is 1, okay, so you write here 4 ratio 1, which means that if 5 patients come to you and if they have mutation, 4 of them will develop a cancer and 1 will be healthy. Okay, so from this analysis, what we understand is that the presence of mutation is very important to development of cancer. Okay, so this need more attention. So this feature specifically, this is our X. Okay, it's X. So this X is important for us to predict the cancer. In the next slide, we're going to see what are the ratios and how these are being used in the logistic regression. So let's start with now the linker function, which connect the statistical function also with the logistic regression to use in machine learning. So by doing this, what we do is that we simply take the natural log of the odds. So for example, here you see that you have formula of your odds And then what you do is when you take the natural logarithm, this is called Logit. So why we use Logit? Because it helps us to uh, minimize or like to put the numbers in the range. Okay, so that can be useful for the probability to convert our score into the probability between 0 and 1. Okay, so this Logit represents this logistic regression. So why it's called the logistic regression? Okay, so regression is separate and logistic is this one. We're going to solve also the regression a bit later. So what we are saying is that, for example, now to link, to make the link between the statistic and the machine learning, we have to convert all the scores into the natural logarithm, which gonna be called the Logit. Okay, so for example, we are continuing with our previous example. So here we are taking the logarithm of our odds. So for example, in the P0, which was absent biomarker, okay? So absent biomarkers means that no P53 mutation, okay? So what was the odds? Was that there was odds between like there was 40% or 0.4 per chances in the cancer, okay? An event that occurred, okay? And then event that didn't occur. So this was like healthy, okay? So when you are like simplifying these, you will get these numbers 2 divided by 3. And when you take the logarithm of this 2 by 3, so you will get these numbers. And now you see that why we are using Logit, because if you are doing this one, this score will not be useful to classify our samples because we need the range, okay? So the range should be like the minimum number, or there should be a smaller number. So these logarithms are more useful, like to simplify our values. Okay, so if you take the logic of biomarker 1, so for example here we had risk of cancer 80% if the biomarker or the mutation was present, and we had 20 patients, no, not 10 patients, which had no mutation, but there was cancer. Okay, so there was the mutation absent here. Okay, so here the mutation present plus they developed cancer. Okay, here there was a mutation present. Sorry, I forget present, but they were healthy. Okay. So when you simplify these numbers, you get the 4 as we already seen in the previous slide. So when you take the natural logarithm of 4, you get this score. When you do calculation, maybe you can verify. So now we have like the Logit score of biomarker absent and biomarker present. Okay? So now we're gonna take the odd ratio. So remember the odd ratio I told you is that like odd ratio is the ratio between two groups. So remember when we were comparing coins and dice. So what was the risk of winning the game? So here uh, we will compare the odd one and odd 0. Okay, so this is the ratio of biomarker. Here we're gonna put, for example, odd one is we have 4, maybe we put 4, and then we put 2 divided by 3. Okay, and then by solving this, we're gonna get this 6. Okay, and when you take the natural logarithm of 6, you arrive at this score. So this is exactly what we are doing here. So for example, this is our biomarker present, and this is biomarker absent odds ratio. Oh, sorry, not ratio. So here is that we take the odds and divided both odds, and we got 6. Okay. Also, you can do by this cross product, where like you have, for example, you have a table, okay, 4. So you're gonna multiply like this, okay, and then divide, and then you get the 6. It's called cross product, but it's okay. You can do simply by this. And then we have, for example, we had binary classification, okay, problem. So we have already labels, which is our supervised learning. So we have 0 for healthy and 1 for cancer. And then what we are doing here is that, no, sorry, this is for X. So 0 means that absent, and this is present. Okay. So now we took the logit of 6, which is 1.7. And so the B1 logit is like as we took is 1. This is just a summary. And this minus 0.405 is the logit of the condition when biomarker is absent, and this is the condition when biomarker is present. Okay? So these are the values. So now we have to do the logit regression. Okay, we did the logit here. We have two logits. Okay, now we have to do regression. We have to simplify the regression. So to do the regression, we use the formula, which is also called the sigmoid function. Okay, so remember that in the previous video, in the class 1, we said that the formula of regression is y is equal to b0 plus b1 and x. Okay, so this was simple regression. So this was making your line straight where you can minimize the prediction errors. Okay, but here in the sigmoid function, we are doing the regression, but with a function which is called Euler. This is the Euler numbers, and it is the constant. I don't remember the constant. I think it's 2.17. Let me check. So it is always the constant you have to put there. Yeah, it's a 2 point. It's always 2.71828. Okay, so this will always be the constant here. So what we're gonna do is, for example, we have to put our values to get the regression line. Okay, the parameter here, the sigmoid function. This is called sigmoid. So this is gonna allow us to get the unknown parameter as we were doing in the regression on the last video. So in the simple regression, we are understanding parameter by this formula, and in the logistic regression, we understand the unknown parameters by sigmoid function. Okay, so what is actually sigmoid function is that here you already have your logit numbers. Okay, so you have to calculate for the both cases or both labels. For example, in the case of biomarker absence and in the case of biomarker presence. Okay, so for the absence, we put in the formula. So you put 1 divided by 1, which will always be constant, okay, which is the same, you don't have to change, plus by E, which is Euler number, okay. But remember that always E have a minus here, okay. So E presented by minus beta 0 plus beta 1 x, okay. So so for now, we have to know the probability of X, okay? So we want to know. So in the absence of the biomarker, okay, we put the formula same and we put here E, and we have to put the absent logit of the biomarker, okay? This was minus, okay? So since we have minus and minus here, so the value become positive here. And so Euler is Euler times 0.4056. This is basically your beta 0. Okay, so the Euler is always this constant. Now remember that this number will not be multiplied with this number, rather it's a times. Okay, so this number 2.71828 times 0.405 and so on. Okay, so this is the times. When you solve this problem, you will get this number. Okay, 1 plus the same formula, and you will get, by solving this number, 1.5. Okay, and when you simplify this, you will get 0.40. Okay, now we have to do for the feature the same feature, but if the mutation present in a data set. So in this case, what you do is you take the regression model formula, okay, beta 0 plus beta 1, so which will be equal to 1.3862, okay. So for the present of the biomarker or the mutation, okay, which is called P1, so we put the same formula. Since this number is a positive and we have negative in the Euler numbers, okay, so positive negative is negative, okay, so this number will become negative. So here you can see that 1 plus 1 and now is 0.25. If you simplify this, you will get the 0.80 score, okay. So how these scores will be used for the classification, we're gonna see later, okay. So now we solve the sigmoid function actually, okay. So next is that for example, now we set a threshold, which is basically the custom. You can set threshold to any number depending on what you are doing research. Okay, so we set the threshold on 0.5. So we are saying is that if the probability of x is like greater than 1 or greater than 0.5, okay, and determining by these formulas, then we will classify these samples. Okay, so this allow us to do the decision boundary. Okay, so I'm gonna tell you soon what is the decision boundary. So for example, how we determine the decision boundary is that when we put when we divide beta 0 with beta 1. Okay, so since we had beta from here is 0.405, and then we had beta 1 value of 1.79. Okay, so in this way we can divide and simplify and we get this, okay, 2.226. Okay, so this will be our decision boundary. So for example, now if your x falls into like less than 0.226, it will be classified as class 0, okay, which is healthy. Okay, if the x is above greater than 0.226, it will be classified as cancer. Okay, so in this way, like we will classify our new samples, our upcoming samples. Okay, so now, for example, I'm trying to explain this decision boundary. So you put here the graph, okay, and here you're gonna put your decision boundary values, which is 0.1, 0.2, and so on, like till 1. Okay, and here are the same from 0.1 to 1. So this 0.5 we decide to put as a decision boundary. Okay, so this will come here as 0.5. Okay, so this is our decision boundary. So what we are saying by this 2 to 6 is that we have to make the boundary end here. So when you like build the S curve, okay, so this should be like this, okay, so it is start here. So this is our decision boundary here by 0.5, 50%. Okay, so now let us start with the samples. If our training, we trained our model, okay, so these are all values that are helping us to classify the new samples. Okay, so these all values are useful. So now we have like trained our logistic regression model. Okay, and now we are giving the unknown sample. Okay, so for example, if your x is a binary number, okay, so binary is for example, you have two new patients. Okay, patient 1 says that the biomarker is absent, and second says it's present. Okay, so what you're gonna do is that all you have to do is you have to calculate these logits as we did from beginning. You have to calculate these since we already did it. So here what is saying is that we have beta 0, which is minus 0.45, 0.4055, and the probability was like 0.40. So since we decide that if the probability is less than 0.5%, so 0.5 means 50%, okay? So the classifier will belong to the class 0, okay? So this means that this this sample is falling somewhere here, okay? So since this is falling somewhere here, we have to classify it as a 0. Okay? And if you have the biomarker present here, so you're going to take the formula beta naught plus b1, and you have the same formula as you had here. Okay, and then by this formula you saw that we got this number. Okay, so these numbers were actually the classification number of any sample. Okay, so if it's a 0.80, which means that this class will be somewhere, this data will be somewhere here. Okay, so now you have classified like two samples based on this mutation. So which is telling you that these are like classified as, if your X value is the feature, if the mutation is present, so your logistic model gonna classify it as a cancer. Okay, if your X is 0, means if your mutation is absent, your classification model gonna classify your samples as healthy. Okay, so now let's see that here we use X as a constant. For example, here we use 0 or 1 as a binary expression. For example, I'm saying that, okay, one patient have a mutation, but still the p53 is working, some like it, not the fully working, but let's say it's working in this expression. For example, it's working at this level. Okay, so now I have continuous value. I don't have the range between 0 and 1. Sorry, not the range, but the value. I don't have fixed value 0 and 1, but I have some continuous value. Okay, which is the most usual case in our biological data. So when in the biological data you have 0 point, like you have continuous values. So now how you're going to calculate and how you're going to classify this is that this Z represent the Euler number is the same. Okay, so for example, in the Euler number, you have mutation, okay, but the mutation rate is 0.3. So what you say is that mutation is present. So you take the formula of the present here, for example, and then you multiply this with its values, okay? So 0.3. So here you can keep put like this. So you have beta 0 here, and you have beta 1, and multiply by x. Okay. So in this, by simplifying this, you're gonna get this value. Okay, and when you put this value, okay, so here you have this value, and now you have to take the times of it. For example, this is Euler number, so 2.712828 and times this number here, okay, times, and you will see that the answer will be 0.53. Okay, so since we build our model with the specific data which say that if the class is less than 50, or if the class is fall into this range, we're going to classify it as a healthy, okay, or no cancer. And if the our decision boundary is going up from 0.5, that means that is class 1, okay, which means cancer. So in this case, we got 0.53, which means that our sample gonna lie here. Okay, so this is 0.53 for suppose, like just example. So in this way, we can like classify unknown samples. So this was the unknown value, and we classify it into the cancer. Okay, we are saying it's a cancer. Okay, so this was the logistic regression formula and the mechanism behind it and how it's working. There are many advantages and disadvantages of logistic regression. For example, now you are saying that when you build the model, okay, the advantage is that you have very simple method in the terms of probability and odds ratio and odds values to see that, okay, this class is being classified by these methods, and you can easily interpret it. So in the end, you can say that, okay, this patient have 53% chances of being cancer, okay? And you can see that 53 is not far from 50, okay? So it's not far from 50. So here we can say that this cancer have very low probability of developing actually cancer, because you have a 50 threshold and it's just 53. So we are not very confident in predicting this sample by determining these values, okay? So this means that either we need more data to train our model and change these values, okay? Or we have to say is that this patient will not gonna develop the cancer, even though it's classified as a class 1, but you see that the number is very low. But it could lead us to the false positive, which is the positive is cancer, and maybe it's gonna tell it is classifying it as a cancer, but the patient will not gonna develop the cancer because the chances are very low. So for example, if the patient have 80%, then we can say confidently that, okay, this patient need the attention that it will develop the cancer at some moment. But for the 53, we can doubt it. So in this way, we can classify, we can see that how algorithms are working behind, and we can interpret very easily. While in the advanced algorithm, for example, random forest SVM, you will not be able to understand how these values were set, for example, these betas, and how parameters was chosen, because they are doing with very advanced techniques, and not all the steps are traceable. So in that way, you don't know that which constants you are taking and which values you are taking to build the model. So that is the advantage of logistic regression.